This video is all about how we can solve trigonometric equations that involve the new functions we've learned in the last video, sec, cosec and cot. So we're going to do 5 examples in this video. Here are the first 2. So the first equation is sec theta is equal to 2, and we're solving this equation between 0 and 360 degrees. So in the last video we learned that sec is the same thing as 1 over cos. So the first thing I'm going to do is replace the sec theta with 1 over cos theta. Next, I'm going to make cos theta the subject. So if I do the reciprocal on the left hand side, I'll do the reciprocal on the right hand side as well. So that gives me that cos theta is equal to 1/2. I can then do cos inverse, and I find that my first answer, the answer that's closest to 0, is 60 degrees. And you can see I've then drawn a cos graph to find the next solution. So I know my first solution is 60 here. The second solution will be 60 less than 360. So 360 take away 60 is 300. So these are the two solutions to that equation in between 0 and 360. Next example, we've got 2 cosec theta plus 3 is equal to 0, and again we're solving that in between 0 and 360. So first thing I've done is I've made the cosec the subject. So I subtracted the 3 from both sides, and then I divided both sides by 2. So on the right hand side I've got minus 3 over 2. Now in the last video we learned that cosec is the same thing as 1 over sine. So I've replaced that on the left hand side. I now want to make sine the subject, so I'm going to do the reciprocal on the left hand side and the reciprocal on the right hand side. So I find that sine theta is equal to minus 2/3. I then do sine inverse of minus 2/3 to get the answer that's closest to 0, which was minus 41.81. Because my minus 2/3 on the y-axis is here. So the calculator's given me this answer here, but I actually want these answers that are between 0 and 360. So, like I say, the calculator told me that this was minus 41.81. So I know that this is also going to be minus 48.1, and that's above 180. So 180 plus the 41.81 gives me the 221.8. I also know that this is also 41.81, and that's less than 360. So if I do 360, take away 41.81, that gives me the second solution between 0 and 360. This is the third example we're going to look at. Notice that we're in radians here, so make sure your calculator is in radians mode if we can see that we are in radians. And the equation is 5 cot theta is equal to 2. So first thing I've done is I've divided both sides by 5 to make cot theta the subject. So I've got that cot theta is equal to 2 over 5. In the last video we learned that cot theta is the same thing as 1 over tan theta. I've then done the reciprocal to make tan the subject. So reciprocal on the left hand side and reciprocal on the right hand side, and that's told me that tan theta is equal to 5 over 2, which I've then done tan inverse on in my calculator. Again, make sure your calculator is in radians mode, and the calculator's given me the answer that's closest to 0, which is 1.19. So on the y-axis I've got 5 over 2 here. The calculator's given me this answer here. We also need this answer over here, between 0 and 2 pi. So we know that this is 1.19. So this will also be 1.19. And it will be 1.19 above pi. So if I do pi plus 1.19, I get the 4.33. And those are the two solutions to that equation in that interval. Next example. We've got 2 sine 2 theta is equal to 3 cot 2 theta. Now, don't worry about the 2 theta on both sides here. That's not going to be an issue. We're going to solve this equation and we're going to get the solutions for 2 theta. And then right at the very, very end of this example, we're going to divide everything by 2. So the 2 theta is not an issue here. The issue is the cot. That doesn't match up with the sine. Now, I know I could turn a cot into 1 over tan, like I did in the last example, but that's not going to really help me with matching it up with the sine. So is there something else that I could turn cot into? Like I say, we know that cot, in this case cot 2 theta, could be 1 over tan 2 theta. But we also learned in the last video that we could also turn that into a cos 2 theta over sine 2 theta. And that's going to be what I do here, because then this is going to match up with this. So that's my strategy. And here's all my working. So you can see on the left-hand side, I've kept it exactly the same to begin with. On the right-hand side, I've turned the cot 2 theta into a cos 2 theta over sine 2 theta. And we've got 3 of those, so 3 of them. Then what I've decided to do is I multiplied both sides by sine 2 theta, just to get rid of the fraction. So that is why on the left-hand side, I've got a sine squared 2 theta there now. Then I've replaced the sine squared 2 theta with a 1 minus cos squared 2 theta, because I know that sine squared can be replaced with 1 minus cos squared. And I've done that so it matches up with what I've got on the right there. So everything is in terms of cos now. I've then expanded this out, so 2 times the 1 and 2 times the cos squared 2 theta. And then I've put everything on the right-hand side. So I've added the 2 cos squared 2 theta. And I've also subtracted the 2. So we've now got this in the form of a nice quadratic, which will factorise. So that's what I've done here. I've factorised this into the brackets here. This factor is going to give me the solutions for when cos 2 theta is equal to 1/2. This factor over here would give me the solutions when cos 2 theta is equal to -2, which we know is not possible. Cos can't equal -2. So straight away, cross that one out. We're not going to carry on with that. But we are going to carry on with this one. So when I do cos inverse to both sides, cos inverse of 1/2 is 60. So that's my first solution. I am now going to do the graph to find all of the other solutions for 2 theta. Notice that I've drawn the graph from -360 to +360. I've drawn the graph twice as big as the range of answers wanted. And the reason I've drawn the graph twice as big as the range wanted is because I know I'm going to divide everything by 2 in a minute. So I want my answers to be twice as big as they need to be. So the first answer on my graph was 60 degrees, which is there. There's going to be another solution here, another solution here, another solution here. I know that's 60. So this is going to be 360 minus 60, which is the 300. I also know that this is going to be 60. So 60 less than 0, which is minus 60. And I know that this is also 60, which is 60 more then minus 360, so minus 300. And then you can see I've divided all of those answers by 2 to get the 4 solutions that are in that range. Last example for this video. We've got the equation 3 sec squared x plus 4 sec x is equal to tan squared x, and we're in radians. So I'm looking at the sec squared and I'm looking at the tan squared. And we're using the identity, the squared identity we learned in the last video, that tan squared x plus 1 is identical to sec squared x. So if I wanted to, I could swap this for a tan squared plus 1, which would be nice because it would match up with this, but it would not match up with the sec x there. So we're not going to do that. Instead, I'm thinking, well, I could subtract 1 from both sides here of this identity, and I know that tan squared x is identical to sec squared x minus 1. So I could replace this with this. And then every term here would then be in terms of sec. So that is my strategy for this question. And here's all my working out. So like I say, I have decided to turn that tan squared into a sec squared minus 1, so that it matches up with the rest of this equation. I've then subtracted sec squared from both sides. So this 3 sec squared became a 2 sec squared. I've then added the 1 to both sides. So we've now got a nice quadratic in terms of sec. Now this quadratic won't factorise like the last one did. So you can see here I've used the quadratic formula. And I've got the 2 solutions from that quadratic formula of the minus 2 plus root 2 over 2 and the minus 2 plus root 2 over 2. Now those are 2 values for sec x. Now I know sec x is the same thing as 1 over cos x. So if I do the reciprocal on the left hand side and I do the reciprocal on the right hand side, then I find that cos x is going to be equal to 2 over minus 2 plus root 2. Which, if you put that in your calculator, you'll find that that is not between 1 and minus 1, so that will not give us any solutions. The second solution to the quadratic was the minus 2 plus root 2 over 2, which again, we're going to do the reciprocal, because we know this is 1 over cos. So if I do the reciprocal here and the reciprocal on the right-hand side, we find that cos x is equal to minus 2 over 2 plus root 2, which is roughly equal to minus 0.585. So I can do cos inverse of that, and I have, and my calculator gave me the answer that's closest to 0 there as 2.20. So on my graph, the minus 5.85 is roughly there. The calculator's given me this solution here. We want this solution here as well. So we know that this is the 2.20. This is also going to be 2.20, and that's less than 2 pi. So if I do 2 pi, take away 2.20, we get the other solution that we need in between 0 and 2 pi. And there we go. So those are 5 examples of using the new trigonometric identities of sec, cosec and cot to solve various types of equations.